The purpose of this talk is to go over actually a project that originated trying to go traditional bid spec and then hybrid or modified itself and turned into an energy service contract to try to do a deeper energy retrofit in 5 buildings in Southern California. Okay, the driver for this project originally was in 2 buildings. There's one central plant that had about, let's see here, it's about 5,000 tons worth of cooling for a building that was 1.3 million square feet and a building that was 1 million square feet. Now the 1.3 million square foot building is 23 stories tall, so it had 300 PSI piping, 300 PSI pumps, and everything else. The other building, the 1 million square feet, is a 7-story classic 70s government construction building. Now they knew they needed additional chiller capacity, so they were trying to go down the path of the original plan spec bid kind of arrangement. So they contracted an outside agency to come in and try to give them some guidelines on what they should be looking at as far as, what kind of equipment should they do, how should they break these 2 plants apart so that one serves the 300 PSI building versus a regular 150 PSI. And somewhere along that process, they realized that the energy efficiency upgrades could actually go towards paying for this project. And they said, wait a second, let's switch and look at this as an ESCO, or as an energy service performance contract. So in 2011, there's original chiller plant design. In 2012, they started to think about going ESPC. 2013, they released the RFP for ESPC, which, given that it's GSA, that's a really involved process. 2013, they awarded us. 2014, we started construction on the phase 1 stuff. Now the phase 1 stuff was only what the original developer had come up with as far as energy conservation measures. We're building somebody else's scope. It's not how ESCOs normally operate. Normally we're going in there and we're assessing the building on our own, trying to figure out what actually pays for itself. Now that was a self-funding project. The key element in it was just the upgrade and modernization of the central utility plant in those 2 key buildings. A couple little ECMs in the other buildings. ECMs are energy conservation measures, in case anybody doesn't know the lingo. 2015, we finished phase 1, started construction on 2A. 2017, we're finishing 2A right now, and starting construction on phase 2B before the end of the year. So given this process, GSA has been looking to upgrade these buildings for 6 years now, just because it started down one path and switched and went down another. Part of that switch in the path is because GSA wanted to accomplish a deep energy retrofit in these buildings, and it's possible. I mean, as it is, GSA's buildings are more energy efficient than the commercial marketplace, typically to the tune of about 25 to 30%. Now in these buildings, we're going to cut their original energy use in half. We're going to see a 50% energy savings. That should reflect in about a 50% savings on the utility bill. Some of GSA's requirements, or actually some of the deep energy retrofit requirements are all listed here. This all comes from the Rocky Mountain Institute. These are the buildings in question. 2 of them are located in Los Angeles, in downtown LA. North LA is 300 North Los Angeles. It doesn't have a different name. And the Roybal building are the 2 that are right next to each other. This is the 24-story, 1.3 million square foot. North LA is just the 8 stories and 1 million square feet, just. Glenn Anderson's located in Long Beach. Ronald Reagan is located in Santa Ana, and the Social Security building is a little 25,000 square foot facility in Huntington Park. This is the original baseline before we started. So the first thing that jumped out at me was that, if the central plant's sitting in 300 North LA, how in the world is the energy bill that even between those 2 buildings? Turns out that they had this design intent in mind. They sub-metered the other side of the plant just for the Roybal building. So they've always been keeping track of it separately. Now normally, if I'm looking at downtown LA, this number is above $2 a square foot. So this is before we started doing anything. This is where GSA is operating. Now, there is roof-mounted PV on 300 North LA. The central boiler plant feeds both buildings as well, so that's why the gas bill only shows up under 300 North LA. Anderson's gas bills include a cogen machine mounted on the roof. I believe that building is about 8 stories tall as well. That cogen machine also has an absorption chiller mounted next to it, so they get some of their cooling from that cogen. This is the original scope of work that was given to us. Relatively simple, with the exception of the big chiller plant modification, and I'll show you the cost drivers for a lot of that next. This is the payback associated with that scope of work. So you can see, I mean, the entire project was looking for about a $620,000 savings figure, and almost all of it was coming from the central plant. The little measures really amount to just little measures. There wasn't a whole lot going on outside of that deep dive into the central plant equipment. Now you'll see a lot of negative numbers up here. It's the first thing that alarmed us. If it wasn't for the central plant overperforming, the project would be upside down. So that's what it really taught us. After the post-installation report, which is a requirement of GSAs, so when you're finished with construction, you have to tell them that you're done and show them what the savings potential really is and how close it's going to be to what you promised originally. We learned early on that we're not going to achieve any real savings without the control systems working. So of those 5 buildings, 3 of the buildings did not have working controls. The central plant was the only thing that was monitored in one of them. After that, you had no idea what was going on in the building. We also realized that even with the central plant modifications that we're doing in the now 5,000 or now 6,000 ton chiller plant in the 2 big buildings, we couldn't tell what was really going on until we got down to the granular data. And we were getting minute by minute data coming out of the control system. Now the ECM up here, that deep retrofit came from was optimization on top of new equipment. So in downtown LA, our driver in this plant is based on the original equipment that's still in service. I'm not sure if I can throw manufacturers' names around, but the taupe chillers have a condenser limit. So they can't take condenser water temperature below a certain below a certain dry bulb temperature, or, well, saturated temperature. And that drives the optimization routines for the rest of the building. So as part of that upgrade, we started measuring a lot of the key plant variables. We got into deeper discussion with GSA about what do we want to do with the excess savings? How do we want to make a deeper retrofit into the building? With the 2 big buildings in downtown LA, ABM actually manages those. So we have direct insight into what the guys on site have problems with out in the buildings. That led to more O&M discussions with GSA about what other saving sources can we apply. GSA is not hamstrung like some other agencies where they can't inject capital dollars into the program. They could buy what they wanted. And us not being a manufacturer, we weren't leaning towards any specific vendor of anything. So we were able to negotiate exactly what the scope of work would be based on what those guys could maintain and deal with. We had to look way outside the box to get to the deep energy retrofit. We did learn right off the bat that commissioning is key. There's an awful lot of those ECMs that if they're not tested and performing properly or not scheduled properly, they'll just never perform. And then we realized pretty early that the only way that we could guarantee success is if we were getting interval data or faster, and we're looking at it continuously. Now, unfortunately, I was hoping to have some screenshots of that interval data and how it works and how it's going to be used for M&V, but GSA being the GSA, GSA IT being GSA IT, it's not set up yet. We have to go through their switches, their routers, their devices. So phase 2 got broken up into 2 pieces. Originally, we were just going to do it phase 1 their way, phase 2 our way. There are a couple of technology items out there like battery storage that is not quite or was not quite ready when we needed to go to construction for phase 2. So we split it apart into phase 2A and phase 2B. Some of the excess savings from phase 2A are going to go towards things that the buildings needed to do anyway. The domestic hot water system, like we said earlier, the boiler plant for both buildings is run through 300 North Los Angeles. That boiler plant feeds heat exchangers in the Roybal building that then deliver hot water to all the lavatories in that building. Not the most efficient way to go through multiple heat exchangers, but it's what it was. So now we will put their own dedicated hot water system over into Roybal. So this is the Anderson building, and this is the original scope of work. You'll notice these numbers can be manipulated based off of where you put the savings. So like the DDC retrofit, GSA wanted to move towards one consistent platform, and that platform is Niagara, or actually Niagara. So it's tritium-based controls in all the buildings. The M&V platform is a Niagara Analytics framework being managed by a third party. And that's what's looking at the fault diagnostics and the interval data. As you expect, lighting is a very fast payback item. Transformers are in just about all of our jobs these days. It's all about the losses. Low flow plumbing, that should be automatic on any job. There are a bunch of different manufacturers and contractors out there that will change either the flush kit or the china itself. There's ups and downs to both. The monitoring-based commissioning is our M&V platform. We did carry a little bit of savings amount, thinking that we are going to get extra savings from being able to tighten up how buildings operate. Retro commissioning was the stuff that we noticed in the control system that was not programmed before. That's your static pressure resets, your cold deck resets, your hot deck shutdowns. We actually do Dyson hand dryers and use operational cost savings. The math is out there and it's quite published, but paper towel use is about a penny per sheet. Figure 2 pennies per person that uses the head, and then you just have to multiply out by what your domestic water usage is to figure out how many people go through how many paper towels. Like I said, each of these buildings wanted to get a chiller replacement accomplished. All of them were in dire need of upgraded cooling plants. Here's the 2A scope of work for 300 North LA. A bit of an eye chart, probably those of you in the back probably. There are a couple of cool ECMs in here, things that we don't normally do, and things that we're starting to do a lot more of. Pressure independent control valves. Anytime you see a low delta T situation around your chiller plant, it's probably overflowing your lower coils, the coils closest to the pumps. Pressure independent control valves, there's a couple of manufacturers in the marketplace. A lot of them call them energy valves. Do get the whole monitoring kit with the valve. The valve by itself is just another control valve. Fan wall retrofit. The 300 North LA's air handling units are from circa 1973. All of these supply fans were single units, that may or may not cover the entire coil. They're just in built-up air handling units that probably, I think most of them are about half the size of this room. So the fans needed to be upgraded. What we did when we went with the fan wall retrofit, and I've got a couple of photos in here later, is it's an array of plug fans. So we'll be able to run VFDs on the plug fans, be able to control the exact volume, be able to get full coverage over the coil. Calculating savings for it was interesting. You'll see some building envelope upgrades in here, reflective solar window tinting. Funny story about the lighting retrofit is as soon as we did the lighting retrofit, or as we're doing the lighting retrofit, this doesn't happen overnight, it's 1 million square feet. We had government employees coming in with big hats and sunblock saying that they can't work under these conditions, it's too bright. I thought that was funny. Threatening to go home. So the first thing we had to do is, as soon as we installed the fixtures, is walk around, and these are all now addressable fixtures, so we just dial into each fixture and tune them down 30%. So this is an LED retrofit versus T8s. And by detuning them down 30%, we were able to actually hit the foot candles that people were more accustomed to. Now, the control system is going to work on top of that, but now that 70% marker is the upper limit on the light output. Let's see here. This is Roybal's scope of work. Roybal, you'll see I wouldn't expect this normally. Roybal was built in, I think, the late 80s, early 90s is when it got occupied. But the VFD replacement in here, a 424-year payback, $1,500 in savings. The reason why that number is what it is, and this is another one of those capital contribution items, the VFDs in the Roybal building, whereas North LA has 4 air handling units per floor, Roybal has typically 32 to 40 air handling units per floor. So a whole lot more VFDs. It's just they're much smaller. They're not the big built-up units. Those VFDs in Roybal had failed. A significant number of them have failed. And based on the age, I'm surprised they lasted this long. So quite a few of the VFDs are actually running 100%. They're just essentially in hand mode. So we carried, again, the minimum amount of savings that GSA would allow us to put in there, and they injected capital to cover the rest. Actually, with this one, I think we blended out quite a few of the other ECMs and still managed to get it to fit in without any additional capital. So this is our original baseline. The 5.2 million was what they were spending in energy, gas, electric. This is phase 1 savings was 620,000. Phase 2A savings is predicted at 1.8. Phase 2 Bravo is almost 500,000. We're going to see almost a $3 million reduction, saving tax dollars. And that's going to pay for the upgrades in these buildings. To make the competition process for the ESCOs at the beginning of the whole transition from design spec bid to energy service contract, the competition process required GSA to actually stipulate the baseline for the central plants in 300 North LA and Roybal. So they gave us these figures. They said right now the plant runs on an average of about 2,500 tons at 1.05 kW per ton. That's all plant accessories. That's tower fans, that's condenser water pumps, chilled water pumps, secondary pumps, and all the chillers themselves. This is where the plants are operating now. Total plant. Basically it's the, it worked out that they were almost identical ton hours between the two plants. But you would compare these numbers. Oh, this is a smaller snapshot. This isn't the whole year of operation. Yeah, we didn't save that much. We just cut that number in half. So this is the plant as it was designed. Actually, this is the whole thing. So this is what was there to begin with, chiller 1 through 5. This is what's there now. We did switch up and went to, everything's water cooled, but we did switch to a couple of magnetic bearing machines for the low loads. There's a slide in here I'll show you in just a second of why we had to look at something that could handle really, really low load. All right, so you notice this is just a simple chart of where the plant operates as far as hours versus tonnage. So typically you're designing a plant for maximum capacity, but the biggest thing that design engineers have overlooked all along or throughout history has been this low load operation side. In the design engineer defense, because I used to be one, GSA said the building was unoccupied at this point. Said there is no low load, or we don't have a load below here. The plant will always operate at least 300 tons and never below. And we noticed that the tremendous number of the hours are from 300 tons and down. So that drove the capacity of the machines that we're looking at. This actually told us that we needed a 250-ton machine in the Roybal building, and we only needed 150 tons over in the 300 North LA building, but the owner being the owner wanted a 450-ton machine that could do a 150-ton load and a 25-ton load. So we ended up with a different machine in there. So here's the bin data. This is how the power matches with outside air temperature and tonnage. But until we could actually see, so when we put in the central plant optimization routine, we were able to start seeing interval data down to the minute level. We realized minutes probably a little too fast. The pumps don't even react. Water can't get around the building. So we started looking at it at 15-minute and then hourly data. So breaking it all down, all the weather data is at hourly level. So breaking it all down, we could actually see where the plant made, where the chiller needed to be upgraded. Which chillers could do the job, which ones couldn't do the job. We have this per machine. This is actually the aggregation of the whole plant. What surprised me is that it really doesn't care about what the outside air temperature is. It's a function of time of day, and it's a function of how many people are in the courthouse. This is the same data for just the Roybal building. This is where we're operating now. So on the very high end, we're hitting 0.7, almost 0.7 kW per ton, which would be normally a flag in our monitoring-based commissioning platform. And at the really low end, we were hitting close to 0.6. Now these are York variable speed machines in the existing plant. This does not include the magnetic machines yet. So this is what we're trying to fix. And we don't really care about this that much, but we do want to make sure that it stays down here. There just aren't enough hours associated with that side of the chart to worry about it. All the hours that we saw from the last chart are down here. So these are the original VFDs that we were trying to replace. These are filament wires. I remember having a calculator like that once upon a way back when. But I was surprised that AABC able to drive with that in it. There's a new magnetic bearing machine. This is a multi-stack. This is what's running 300 North Los Angeles now for probably half of its occupied hours and all of its unoccupied hours. There's the new YMC squared for Roybal. You have to touch this machine to know that it's running. Here's a plug fan system. So this is a fan array. This used to be one big, I think this was a 75 horsepower fan. And these are 310s, or 610s. Smaller fans, easier to control. Each of them has a VFD. They're all arrayed together so they get the same power, get better coverage over the coil. And we're doing a better static pressure control job than we could with the big forward curve fan. This is remember at Reagan we told you that the control system only monitored the central plant. The first thing that jumped out at me when I looked at this thing is that the smallest chiller, the 175-ton chiller, has 35,000 run hours on it. Chiller 2A, next the 400-ton chiller, has 14,000 hours on it. Chiller 2B, 7,000. Chiller 2C has never run. Yeah. So in the load analysis so this is the original plant. They were all York machines. It was a York plant. They're all variable speed. We only changed out the one machine because there really wasn't enough runtime on the other ones. Absolutely not enough runtime on this one. And we upsized it to 250 tons. Made it magnetic. It's a York YMC squared. This is how the plant operated before. You had that, we'll go back. We have this 175-ton chiller trying to do all of this load. And it just goes asymmetrical when it hits 50 tons. Has a hard time stopping from surging, has a hard time meeting building load. You have all the rest of the plant is trying to compensate for it. This is what chiller 2A is doing. Unfortunately, when chiller 1 shuts down, this machine has to pick up this point, and then it takes off. So the perfect solution for us was to find a 250-ton chiller that could do that job. Here's the Anderson plant, including the constant speed absorption machine. The funny thing about that ECM when it was done in the previous energy service performance contract is that the The cogen machine that's on top of Anderson cannot run outside of occupied hours. It generates more power than the building uses. So it can only run from 8 to 5. And it can only run when, well, it's a Genbacher. So it can only run when Austria sends it parts. So in here we actually switched chiller 1 and chiller 3. Chiller 2, yeah, chiller 1 was the one that died. The plant originally relied on that. There was no central control system in this plant at all. So the operators typically turned on the chillers based on weather. So if it's going to be a hot one, they ran 2 machines, which shows up here. This is the efficiency of the plant. This plant screamed low delta T problem because there was no central control plant or control system. They were overflowing the chillers. Surprisingly, the building stayed pretty comfortable. I guess it's a perk of living in Long Beach.